In this video, we're going to continue AC circuits. We're going to try and be able to describe by the end of this video a series RLC circuit. So a resistor, inductor, and a capacitor all connected in series across an AC source. Remember last video, we did each circuit element separately across the source. So the first part of the video is just going to look at a resistor and a capacitor in series across the source. And then the second part will be generalizing and including an inductor as well. Okay. So the first thing to realize is that in this circuit, the current everywhere is the same. So I as a function of time is going to be sinusoidal, just like before. But it's the same everywhere in the circuit. So so it has some. So we use lowercase I for the time dependent quantity, and then maybe capital I for the peak value. Cosine of there can be some offset from the omega t. So actually your book doesn't, your book doesn't write the offset explicitly because we don't want to introduce a convention that's going to contradict this thing right here. So I'm probably going to hold off on writing the function. But you do have current as a function of time, sinusoidal, and not necessarily in phase with the source voltage. So there's only one current in the circuit, but there are multiple voltages. So there's the voltage provided by the source, which is some peak value times cosine omega t. And that instantaneous voltage of the source is the sum of the voltages across the resistor and the capacitor. So the resistor has some voltage across it as a function of time, and the capacitor has a voltage as a function of time. And it's the sum of the two that's the same as the source. So like going from A to B, point A to point B, you can go across the source and get this, or you can go across the capacitor and the resistor, but you have to sum up those voltages to get the total. Okay, so we're going to use what we learned before to analyze this. And in particular, a phasor diagram is going to help a lot because these two quantities, and actually all three quantities, are not going to be in phase with each other. So actually any two of these are not in phase with each other. So we use phasor diagrams to help simplify some of the trigonometry because like trying to add together cosines that don't have the same phase can get pretty complicated. So the way we do this, and your book describes exactly the order in which we do this. Because the circuit elements are all connected in series, we're going to start with the current phasor because the current phasor is the same for all three circuit elements, the source and the resistor and the capacitor. So we're going to draw each phasor relative to this. In particular, so the first thing we draw is the voltage across the resistor. And because of Ohm's law, so V equals IR, the voltage across the resistor at any moment, so lowercase r would be, so V equals IR. And it's just the resistance of the resistor that's constant. And so these two things are in phase. They're just off by a constant proportionality that actually has some units here. So they don't have the same units, but they are in phase. So this is the resistor phasor. And then we saw in the last video that if we're looking at the voltage across the capacitor, it actually lags the current. Remember, the current leads the voltage by 90 degrees for a capacitor. So the current being delivered to the capacitor or going through the capacitor and the voltage of the capacitor are off by 90 degrees. Okay, so you have to imagine all of these things. So it doesn't really matter what the starting point was. That your book drew it here, but it didn't really matter. We could have had any starting point. They could have drawn it over here, in which case we would draw the voltage across the capacitor here and the current and the voltage across the resistor here. So we could have done this too. It wouldn't have mattered. Okay, so now it's the sum of the two voltage phasors for the resistor and the capacitor that describes the source EMF. So notice how the source EMF phasor is the sum of those two phasors for the other circuit elements. So you have to add vectors in this phasor diagram. You're adding the two vectors. And notice how this is giving something else with a different phase relative to the other two. So the source lags behind the current, but the source also leads the capacitor voltage. So you can kind of see as this thing rotates, which one takes on their maximum value first. It's this one first, and then this one, and then this one. So the actual angle here, so the angles like either here or this one, these depend on the relative magnitudes of V sub R and V sub C. So we'll look at these two values in just a second. But whatever values of these are, you would add together these two phasors, which are at right angles with each other to get the source phasor. So if you plot the three voltage phasors, they form a right triangle, and the hypotenuse is the source voltage. So this will relate, if you know any two of these things, you can solve for the third one using the Pythagorean theorem. Okay, so these are the peak values. It's also true that instantaneously, maybe for emphasis, a different color. So the value of the source at any one time is equal to the sum of the resistor's voltage at that time plus the capacitor's voltage at that time. So this is true instantaneously, but if we're relating the peak values of these quantities, you have to add them in quadrature like this. So this isn't, these are two slightly different formulas. I mean, one is at a particular instant in time, and then this one right here is looking at the max value of these quantities. So maybe this one would be closer to the, okay. So we're going to use Ohm's law. So the voltage across the resistor. So now I'm plotting the maximum value of this, right? Capital I and capital V. Voltage across the resistor is related to the peak current that goes through it. And then the voltage across the capacitor, remember, was I x C, where that was the capacitive reactance. That was I over omega C. So we're going to plug these two quantities into this formula right here to relate the peak voltage of the source, E naught, with some of the other quantities in the problem. So the current we don't know, but we do know the resistance, the capacitance, and the source frequency, omega. So if you plug those in, you get this formula. And solving for I, you can get this right here. So this is the current in the circuit, I, versus as a function of the source peak voltage, and then all this other stuff. So we also write this as E over Z, where Z is called the impedance of the circuit. So and this will come up later with when we combine all three circuit elements, right here. But this impedance is R squared plus XC squared. This is sort of giving the overall effective resistance in the circuit. So we would use this impedance combined with the formula that the source EMF, V equals IR basically, but it's IZ for these AC circuits. So this is a generalization of like Ohm's law, but for AC circuits where you can have more than one kind of circuit element, more than just resistors. So this is the overall impedance. It's like an effective resistance, it's in ohms. And it's this combination. So the effective resistance could be dominated by the resistor or the capacitor. It depends on the frequency, because the X sub C depends on frequency that we see right here, 1 over omega C. If you take this current and you plug it back into these two, you get the voltage across these two circuit elements, the voltage across the resistor and the capacitor. And those both depend on frequency. And so that's what your book talks about next. It talks about what are the voltage across those two things as a function of frequency. And you can see at low frequencies, the capacitor has the voltage, the main voltage across it, and the resistor has little voltage across it. And then that flips at higher frequencies. So at higher frequency, it's the resistor that has most of the voltage in the circuit. So what we can do with this fact, and this is where the two values meet. So there's a special frequency where the two cross over. This is called the crossover frequency. But we can use this fact to create filters. So if you have a source that's operating at a frequency either much below that crossover frequency or much above the crossover frequency, you can use the fact that most of the voltage is across one of the circuit elements to block out the other one that you don't want. So for example, in this circuit right here, so what happens is that, so let's look at part A, the figure in A in particular. So if you look at A, there are two sort of signals. There are two possibilities for what the source could have. So the source could have a frequency that's much less than the crossover frequency, or much bigger. So let's look at the two cases. So if the frequency is very, very small, let's remember what happens here. So most of the voltage is across the capacitor. Remember, the reactance of the capacitor is very big. For omega small, 1 over omega c is very, very big. And so most of the voltage is across the capacitor right here. So if you take the circuit and you touch the two ends right here, you can get basically the voltage that was across the source is also across these two. So for small frequencies, the voltage across the capacitor is about the voltage of the source. And so the capacitor will act like the EMF source. Okay, so low frequencies are allowed to pass. But then for high frequencies, the voltage across the capacitor is about 0. Most of the voltage is across the resistor. So the reason for this is that if the frequency is really, really big, the capacitor basically acts like a short. And so those high frequency signals can just remain in this loop. And most of that voltage drop would be across the resistor for those high frequency signals. So basically the high frequency signals are going to stay in here and they're not going to be transmitted outward. The capacitor lets those through. If you want to create the opposite, if you want a high pass filter, you would just connect the output voltage across the resistor, because it will do the opposite in terms of what signals it'll, in terms of when it has a big voltage across it. Okay, so now putting all three of these things together, series RLC circuits. Again, we're staying with the case where all of these elements are in series. So we start with the voltage phasor, and then we draw 3 on top of this. Now the inductor is going to lead, the inductor voltage phasor leads the current, and the capacitor voltage phasor lags the current. So when you draw all 3, it looks like this. So again, it doesn't matter where you started with, it doesn't matter I, but it does matter that, wherever you started with, the inductor phasor needs to be ahead of the current phasor. So when you add those 3 phasors together, the one that's along this axis is VL minus VC. So if VC is bigger than VL, it's actually pointing the other way. It's actually pointing down like this. So when they drew it, they're just assuming VL is greater than VC, just to be able to draw the vector, because it would be confusing if they tried to draw both directions at the same time. So when you add these 3 vectors together, you get the source frequency. Because again, like going from here to here to here to here, you're adding together all 3 voltages across the 3 circuit elements, and that's equal to the voltage of the source. So you have to add all 3 voltage phasors this time. And again, that gives you a right triangle that will allow you to relate the peak values of the voltages across the 3 circuit elements to the source voltage, E0. So we do the same sort of trick that we had last time. So we know VR is IR from Ohm's law. We know VC is I X sub C, or I over omega C. And the voltage across the inductor is I omega L. So we plug those 3 things into this formula to relate E0 with the current in the circuit. And we get this right here. We get I is equal to E0 over Z, again, the impedance, where the impedance is square root of R squared plus, and then it doesn't really matter the order right here, but it's a difference in the reactances of the inductor and the capacitor squared. So because you're squaring it, that's why I say the order doesn't matter. The order does matter for this phase angle. So maybe switching thoughts here. The source voltage is E naught cosine omega t. The current phasor is some max value cosine of omega t minus phi. So we're going to define this phase angle phi to be the angle by which the current lags the source. So in this picture right here, this angle right here is phi. It's the angle that E naught is ahead of I. So if phi is positive, then it looks like this. If phi is negative, then the source voltage phasor is actually lagging behind the current phasor. So if phi is positive, the current lags the source. So in other words, like if you look at this, it peaks at t equals 0. If you ask when this peaks right here, you have to wait a little bit of time. You know, say if phi is 10 degrees, or I guess pi over 18 radians or whatever. You have to wait a little bit of time before this becomes 0 and before this becomes maximal. So that's why we say that the I is lagging the E. That's why it's a minus sign right here. So if we know the relative values of the V's, we can actually solve for this angle. So this angle phi is also this angle in the right triangle. So we can write an equation that's, you know, tangent phi is opposite over hypotenuse. So it looks like this is VL minus VC over R. Over V sub R. And actually, if you plug in these three things into that formula, you can also write this as X sub L minus X sub C over R. So if you knew the reactances of the inductor and the capacitor and the resistance of the resistor, you can solve for the phase angle using that relationship. Okay, so the phase angle tells you how much the source is ahead of the current, and the impedance gives you this overall effective resistance that will relate the source voltage to the total current going on in the circuit. So the bigger the impedance, the more effective resistance there is. The last thing is called resonance. So you'll notice that the impedance is a function of frequency. So right here, the impedance is a function of frequency because those X sub L and X sub C values depend on frequency. Resistance is independent of frequency, so that's not going to affect it. Also, notice that the impedance is at least R, and in general bigger than R. But the smallest value of the impedance would happen if this piece right here could be 0. Could be 0. So if that were 0, this would minimize Z, the impedance, and maximize the current in the circuit for a given E naught. So if you look at what the current in the circuit is as a function of frequency, you can see that it's peaked at some value called the resonant frequency. So this is the frequency where those two things are equal, where X sub L is equal to X sub C. So this is the special frequency that's going to maximize the current. It's where the impedance is minimized and equal to R, the resistance of the circuit. And when you set those two X values equal, which is done right here, you can solve for omega and you get this right here. And this should look familiar from LC circuit oscillations. This is the same quantity, 1 over square root of LC. So this is called the resonance frequency for the AC circuit. This is where the circuit is happiest. It's able to do a lot of current, you know. So otherwise you're driving it too fast and the inductor is not happy. The inductor is blocking there from being much current. And if you go too slow, then you're building up too much charge on the capacitor, and the capacitor is kind of fighting your ability to switch directions very quickly. So there's some happy medium between the two, and this is why it depends on the values of L and C. You'll notice that this resonant frequency is independent of the resistance of the resistor, but the value of the resistance tells you how sensitive you are to being at the resonant frequency. So the lower resistance you have, notice how sharply peaked this curve is. So resonance is a more and more important thing the smaller the resistance of the circuit. And when R was 0, it was the only thing that was important. Remember, that was the LC circuit oscillations. They were happening right at omega naught. this is a lot. I think this is enough for this video. Let's look at an example problem that will revisit some of these topics. For this RLC series circuit, in this example on the left, we want to solve for the impedance of the circuit in the first part. So the impedance is going to be the square root of r squared plus x sub l minus x sub c squared. All right, so let's look at the two values, or we need to find what these values are. We already know what R is, but L and C are going to depend on the frequency of the source. So X sub L is omega times L. So it looks like this is 100 radians per second. So SI units there, SI units here. And as long as everything's in SI units, we're going to get a certain number of ohms for a reactance. It looks like this is 80 ohms for X sub L. X sub C is 1 over omega C. So what looks like 1 over 100 times C is 50 microfarads. So 1 over micro is 1 over 10 to the minus 6, or 10 to the 6 on top. So this is times 10 to the 6 ohms. 10 to the 6 over 100 is 10 to the 4. 10 to the 4 over 50 is 10 to the 3 over 5, or 1,000 over 5 is 200. This is 200 ohms. Okay, so plugging that in, it looks like 80 minus 200 is negative 120 ohms, but we're going to square it, so it doesn't really matter the fact that it's negative 120. Negative 120 or positive 120, it doesn't matter. Z is going to be square root of the resistance value is 50 ohms. And this quantity right here is 120, is the difference between 80 and 200. So I might as well just leave the minus sign in there, but it's not going to matter because of the square. And you'll notice that, or maybe you remember from math class, from all your examples in math class, that there exists a Pythagorean triplet, 5, 12, 13. So this is that ramped up by, or scaled up by a factor of 10. But this is 130 ohms for the total resistance. So it looks like we're done with that. So bigger than the resistance, which is a good check. You're never going to get an impedance that's smaller than the value of the resistance for a series RLC circuit. Okay, does the source EMF lead or lag the current? So for part B, it might be useful to draw a phasor diagram. They almost always help with this sort of thing. So you have some current phasor. Yeah. You have some current phasor, and it's also going to be the voltage of the resistor phasor. And we have two more voltage phasors, right? The V sub L and the V sub C for the inductor and the capacitor. So V sub L, so actually let me mention one thing here. So V sub C is I X sub C, and V sub L is I times X sub L. So we computed the two X values and we saw which one was bigger. We saw X sub C was bigger than X sub L. So the reactance of the capacitor was bigger. And if we look at, the reason I just wrote this formula down was that a bigger X value means a bigger voltage value, peak voltage across that circuit element. So the voltage across the capacitor is actually a lot bigger than the voltage across the inductor. So this is the voltage across the capacitor, voltage across the inductor. And so what happens is that if we drew the sum of these three phasors, the sum is actually going to lag behind. So the sum of these two is maybe right here, and then we're drawing the sum of this and the voltage phasor. It doesn't have to line up with the horizontal. So this is the V total. So adding the three voltage phasors, which is also the source EMF, E0. And it looks like in this circuit, the source EMF is lagging the current. You can see how it's behind the current phasor. And this is all due to the fact that V sub C is bigger than V sub L. The capacitive reactance is bigger than the inductive reactance. So it turns out this happens because, so going back to this phenomena of resonance. So this goes back to, if we were at resonance, then those two voltage values would be equal. V sub L would be equal to V sub C. The fact that they're not equal means we're not at resonance. So the next question to ask is, are we above the resonant frequency or are we below the resonant frequency for this problem? And if you look at this formula right here, you'll see that X sub C is too big compared to X sub L. So try and guess whether our omega is too big compared to resonance or too small compared to resonance. Maybe pause the video and guess. Really, you'll want to look at these two values. So here it looks like the reason X sub C is bigger than X sub L is because we're below the resonant frequency. So notice the 1 over omega C. If you're below the resonant frequency, then the fact that it's on the denominator means this is bigger than this value right here. So it looks like as an extra piece of information, like part C, we are below the resonant frequency. So the capacitor is not happy in the sense that it's blocking things from happening. It's switching polarity. The battery is switching polarity. The EMF source is switching polarity too slowly, and so the capacitor is building up a voltage difference, too much charge, relative to that resonant frequency. All right.